printing. All right, so let me restart. So welcome to the Ethernet Alliance's Technical Exploration Forum 2021, The Road Ahead. So today we have the welcome keynote presentations and the market need the next Ethernet rate panel. So my name is Peter Jones. I have the honor to be the Ethernet Alliance Chairman, and I work for Cisco Systems. So let's get into what we're doing. So the Ethernet Alliance, right, we are a global community of end users, system vendors, component suppliers, and academia. What this means is we really represent the Ethernet ecosystem. Now, our mission really is to promote the value of Ethernet and to accelerate industry adoption and remove barriers. Our goal is to make it clear the value of Ethernet and to help move Ethernet along. You can see our current membership. We have a pretty broad membership from principal members, associates participating in consulting. We really cover the entire spectrum of both Ethernet vendors and a bunch of partner organizations. So a little bit more detail into our strategy. You know, we really want to support the development and expand the ecosystem, right? Some key things we do. We do interoperability testing, right? So PlugFest is one of our key things. Why does this matter? We want to make sure that when technology gets to our users, it's fully ready to go. We want to basically meet that tradition of Ethernet of plug it in and it just works. We do interoperability assurance, right? We have launched a PoE certification program. Gen 1, you know, dealing with AF and AT has been up and running for a while, and Gen 2, Protocol 3BT has been launched. We do interaction with other industry organizations. This could be SIGs, applications, and MSAs. We really try and build consensus amongst a whole lot of groups for how the best to apply Ethernet. We have global membership, and we do thought leadership. So this would be an example of the technology exploration forums. We really try and do technology incubation because we can bring together what the market and users really need. And we do promotion of Ethernet with things like we talk to industry analysts, with education, so webinars, this type of event, and we do marketing. So we'd show up at trade shows, we'll do white paper and blogs. So we're really out there to tell the story of Ethernet. I want to quickly dive into the PoE certification. So we're an award-winning program. So we picked up the Cabling Installation Magazine, the Innovators Award in 2020. And the goal, again, is to basically bring the PoE certification based on the IEEE standards, so we can start getting even more predictability and reliability of these devices that come out to the market. Because PoE is becoming much more common to power all sorts of things, and we need to preserve that public confidence. So you can see the program benefits, and that program is very exciting. So here's the quick schedule for the week. So we're on Monday, so this is welcome remarks. We'll do the Beyond 400 Gig keynote. Then we'll look that's with John D'Ambrosio, and we'll look beyond this from Rakesh for a system perspective. Then at the end of the day, we have the market need, the next rate panel. So you can see Tuesday and Wednesday. Tuesday's new applications and high bandwidth. Wednesday's beyond 100 gig electrical. Thursday is next gen optical interfaces. On Friday, we'll get in with our test and measurement colleagues. Here's a little more detail what there is today. Welcome remarks. Then the presentation from John D'Ambrosio, chair of ATEL 3 study group on beyond 400 gig. Presentation from Rakesh Chopra from Cisco Systems, again, looking beyond 400 gig. Then we'll do the next rate panel, which is myself moderating, and Sameh from Dell'Oro, David from Juniper, and Vlad from LightCounting. I'm going to skip over the schedules for the next couple of days. And what I really want to do now is introduce John D'Ambrosio to his presentation. So John has a long and deep history with Ethernet, right? He's chaired a number of IEEE study groups, including the current Beyond 400 Gig study group. He was also the chair of the Ethernet Alliance from 2011 to 2019. So John, welcome to the TEF, and please take it away. John, are you with us?
Hello, Peter. Can you hear me?
I can hear you. I can also see you. And you.
Yeah, sorry. There's a slight delay in going live on video. So thank you very much. I'd like to thank the Ethernet Alliance for having me today to talk about the Beyond 400 Gig study group, 400 gigabit per second Ethernet study group. So thank you very much. It's just starting, and there's so much to talk about today. So let's get started. As Peter alluded to, I have chaired a number of task forces inside of IEEE 802.3 Ethernet. There's 3 of them I'm actually doing right now. In addition to that, I was the chair of the 200 and 400 gig task force, and the task force has developed 40 gig and 100 gig. I guess I should probably, I'm not going to spend too much time on myself, but before I get started, just since this is about an IEEE standard, I need to use a normal disclaimer that anything you hear me say today is my opinion, and I'm not speaking on behalf of IEEE. So where did the need for 400 gigabit per second Ethernet start? Well, I think we're all familiar with the term up and to the right, and that's what we've been experiencing over the past several years. In September of 2018, about 9 months after the 400 gig standard had been completed, a group of people got together and thought, you know, we really do need to keep an eye on what's happening with bandwidth trends once again. And we started in the IEEE to then do what's called Ethernet Bandwidth Assessment, Part 2. And what I'm showing you here is the punchline, the conclusions of that group, where basically what we showed was that compared, if you look at traffic in 2017 and compare where it will be in 2025, the values were anywhere from roughly 2.5 to 55 times the amount of traffic that these different application spaces were looking at in 2017. And you'll see over on the right, I've shown 800 gig and 1.6. And the point of including those in there was to give a point of reference. So if you look at 800 gig, people see that, you know, that's very low compared to where all of the other bandwidth is. If we look up here, and this is kind of grayed out here to just kind of show the trends of what will happen with Ethernet. But if you were to look at, you know, 800 gig and then go look at data centers have much higher growth rates than what Ethernet is going to be experiencing. Even 1.6 terabit isn't growing as fast as all of the traffic is. So there was a lot of concern about this. And one of the things that came out of the discussion of this data was that we really need to get started. And the way that you do that in IEEE is to have what's called a call for interest and to form a study group, which we did in November of last year, and the study group was formally approved in December. So we kicked off that start of that standard in 2020, and if we look at an estimate, 5 years is a reasonable time to assume how long it'll take us to get a standard done. So in 2025, we got to get started. We got to get these things done because traffic is just going to keep going up and to the right. And remember, that 5 years is only an estimate. But some of the problems that we're going to be talking about here, it's very plausible that we could have a very large project that could go on for more years, or projects that may span more than 5 years. So there's a lot of work, and I'll kind of touch on that in a second. So this is the charter of the study group. It's actually unique for a study group of this type. Normally, when you have a study group where you're going to go look at a next higher speed, that really is the charter of the study group. Go look at a higher speed than whatever you have right now, or go look at a specific speed, as was the case with 400 gigabit Ethernet. In this case, it was recognized that we might develop some signaling technologies as we develop 800 or 1.6 or whatever speed that might be applicable to existing Ethernet rates. So you can imagine, for example, if we were to say, oh, we're going to develop 800 gigabit Ethernet based on 4 lanes of 200 gigabit per second. Well, that 200 gigabit per second would then be applicable to 200 gigabit Ethernet and 400 gig Ethernet. So we actually have a unique charter for a higher speed group where we're actually going to potentially be retroactive to existing rates if we develop signaling technologies that are applicable to those rates. Okay. For your own edification, I've included links to the web page and to the reflector. I would encourage people to sign up for the reflector, get involved, and you'll be able to download material from the group on the web page. Now, there's a real simple basic math for Ethernet nowadays, and we've been using this chart for some time because it makes sense, right? So on the bottom, on the x-axis, we have the signaling rate per lane, and then on the y-axis, we have the interface width. Okay. Now, it's a basic multiplication. As I say to my kids, I can't do calculus, but I can still do this math nowadays. So 4 lanes of 200 gig, I've got an 800 gig solution. Or maybe 8 lanes of 100 gig, I've got an 800 gig solution. Or 16 lanes of 100 gig, 1.6. It's really that simple. And I say that kind of funny, right? Because 16 times 100, yeah, that's simple math, but there's a lot of other issues that will go into it that the study group is going to have to consider. I think that's what I'm saying is the work needs to begin, right? And by the work beginning, we're not talking about the work to define the standard. We're really talking about the work of the study group. And the work of the study group is really to define the project. And that's very different, right? So we have to figure out from this whole, if you look at the Ethernet ecosystem nowadays, there is a whole bunch of different physical layers there, starting from chip to chip and chip to module, electrical interfaces. There's physical layer specifications for copper cables. I don't think we'll be doing any twisted pair this time. So I don't think PoE is going to be applicable in this case to 800 gig Ethernet, at least yet. But then there's a whole bunch of multi-mode, optical, single mode fiber, duplex fiber, parallel fiber, DCI interconnect. So there really are a whole host of physical layer specifications that the group is going to have to consider for 800 or 1.6 or whatever speed we decide, or speeds, right? So these are like very key questions. And in addition, I think one of the other factors that's outlined there is that it's getting harder to do direct-to-text signaling, and some people are beginning to wonder, well, okay, is coherent signaling something that we're using for DCI in the CT and CW projects right now? Does that have a place in this project? Are we going to see some perhaps physical layer specifications for the typical Ethernet reaches below 40 kilometers? And really in these type of projects, it's normally below 10 kilometers, where coherent signaling may play a part. Don't know. That'll be something that the study group will need to answer. So I kind of just rattled off all of those things in my head, but here's just a potential target list of objectives. Now these are just there's other objectives besides these, but these are really the key ones, right? Are there any electrical interfaces are we going to do? Are we going to look at any physical layer specifications? As I said, backplane and twin-ax, those could come in. I would say backplane is typically another project that comes a little bit later after the original kickoff speed. Twin-ax has been in there sometimes, sometimes not. And then multi-mode and single-mode fiber solutions, even DWDM systems, all of this stuff is fair game. And the objectives themselves may include lane count. So if we're going to do perhaps a parallel fiber solution such as PSM4, maybe that will show up in the objectives. That's something that we'll need to be looking at. And as I said, we do have the ability, if we develop signaling for the higher speed that's applicable to lower speeds, that we could see some objectives for 200 and 400 gig Ethernet possibly even show up. Given that a lot of work has already happened with 100 gig, I don't think we'll see too much retro from 100 gigabit per second signaling, because that's pretty well being developed in the project now. All right, so a whole list of things that we need to think about and to go through. Now, I know I don't want to go too much into the sausage making, but the role of the study group is not to write the standard. It's to define the project. And part of the way that we do this is through defining our objectives and then writing our project authorization request for PAR, and then also writing what's called the criteria for standards design. Now, this is the CSD, but it contains something that people familiar with Ethernet may know, which is called the 5 critters. And there are 3 that are very familiar. You can think of them as the tripod upon which this whole effort will be based upon, really. 1 is there broad market potential? 2, is it technically feasible? And 3, is it economically feasible? We really have to answer those questions. So it's not just a matter of saying, hey, I want to define a project that's going to do this objective. Well, you need to make sure that there is a whole bunch of applications and vendors and users who want that solution. And you need to make sure that it's technically feasible and economically feasible. These are the ways that 802 essentially judges projects to start. We'll have to answer those questions. All right, so that's really more part of the project. And if you want to look at what the key questions for the group are to answer, I kind of put it up in 3 ideas. 1, what's the next rate or rates? And, people need to understand that we could be doing more than one rate. If you look at the last two speed projects, 100 gig started off, and then we added 40 gig, and then 40 gig became more than just what it was, and it moved from just being a computing solution to being a networking solution. Then we decided to do 400 gig, and we got that project started, and then we decided, oh, we're going to add 200 gig. I like to think that we get smarter, so the scope of the study group is open. So we could actually define, I would think, 2 speeds possibly. I don't think more than 2 at this time, but I could very easily see us doing a new project where we look at 800 and 1.6. The other thing that we need to consider is, and I kind of touched on this already, what physical layer specifications will be selected as objectives. And this is normally where I would say there's a lot of debate in terms of what has to go into the project or what people agree to go in the project. Let's remember in 802.3, all technical objectives or technical answers, questions, however you want to look at it, require 75% consensus. So there's a lot of people that have to vote and believe in whatever we're going to put into this project in terms of our objectives. And then finally, how is the PAR going to be written? And I phrase it that way because I think a number of people looking at this project recognize the scale of this project. I've jokingly joked with people already that this is my last project because this thing could go on forever. There are a lot of different variants that could go in here. It would be very easy to see 800, 1.6, DCI, all of these different things come in, or to have a multi-tiered single project and maybe things get spun out. That's a distinct possibility. We're doing that right now with the CT and CW projects, which started off as part of another project. So we really need to think about how are we going to best manage this project, not just for our own resources, but what makes sense for the industry. And finally, I'm going to get the right page here. Sorry. So finally, I want everybody to recognize we're just starting this journey. First steps. If you were to go and look at when we started 100 gig Ethernet, that started in 2006. And that, when I say started, that's from the formal CFI. The actual discussions about getting stuff started happened in November of 2005. I was there. I remember. 2006, we'll start from there. It's 2021 now, 15 years, and we're still finishing up work. There's still several projects underway targeting 100 gig. And if you were to go and look at that, I went through and I looked at all of the different projects that 802.3 has done since that time, and I counted 8 different projects. 8. Okay, so it's a long journey. Things may not all go into the first project, but I'm sure that there will be multiple projects eventually that we will all need to consider. And as I'm saying that, to me, I've talked a lot about the physical layer in this presentation, but what we really need to make sure that we do as a study group and a future task force is to build the underlying architecture. And that architecture needs to be flexible and needs to support multiple generations of solutions, because I can assure you, changes will come, and if you have a strong architecture to begin with that's flexible to address it, it makes life so much easier from a standards perspective, development perspective, as opposed to having to figure out, well, how do I fix this to get it to do what I want? So there's a lot of work that will go on in the coming days, but I want everybody to keep in mind that Ethernet will be here for a while, and the development of this project is going to take a period of time. And we need to make sure that we get things done right to begin with to build upon it for all of these future projects. And with that, Peter, I think I'm within my 15 minutes, so I'm going to say thank you to everybody.
So, John, thank you very much for the presentation. And I will note that actually, yes, in fact, you are. You've even delivered early. So what I wanted to ask, John, given you got so much experience here, so what do you think are like the key couple of decisions we need to make? And what do you think is going to help us make them in reasonable time?
Yeah, that's a good question. I mean, obviously the speed is a key question for a number of reasons, right? Because it's going to set up a lot of things that we do here, as well as looking at things that make sense to do. And there are discussions that need to happen here. I'm less concerned about the technical aspects of things at this time. Honestly, at this point in time, if we have 2 solutions, 3 solutions, 4 solutions, that only strengthens what the group is doing. We don't need to select right now. So there's no decisions in terms of, what the right technical solution is. That's not the role of the study group. What the role of the study group is, well, what physical layers that we need to do. So I think it's the speeds and the physical layers where our big problems are. And once we do that, then I think, and I know we've already had some conversations about this, thinking about how to organize ourselves to address this. It may make sense to keep everything together to begin with, and then to go along and have all the considerations that we need to do, and then figure out, is there a better way to divide up the project, or will that happen as a matter of timelines, diverging timelines? So right now it's really just objectives, Peter.
So that makes a lot of sense. I have a question that's come in. I'm going to ask you to answer it succinctly. So the question is, right, why only 500 meters for greater than 400 gig? So that's the question from someone. And so I think this is in your slide at the minute where it's showing the multi-mode and single mode.
So this is really kind of a typical layer diagram, and it's looking at a lot of the solutions here. And what we see in a lot of the leaf and spine where we want to go to greater than 400 in this connection is the use, really I would say there's a lot of parallel solutions there. And when you look at the parallel solutions right now that are happening at 400 gig, they are based up to, you can do 50 and 100 is being developed in the DB project, and 500 meters was actually an objective in the BS project. So this is really kind of more of a historical line in the sand than stating anything in terms of what objectives will be. So it's really just looking backwards.
So this, to some extent, this is the classic. You start by saying something, and then everyone works around it.
I look at more like this is a straw man. Where are we today, and where do we want to go? I mean, I've already heard people talking about that 500 meter number going up to 2 to 3 kilometers using parallel fiber, because I think a lot of people do recognize the challenges with the duplex solutions. And I've heard some people actually saying this. I think that would be a very good debate. So please, as people are looking at this, don't think that this chart says, oh, this is what we're going to do. No, it says this is what we've done. And there's a big difference there.
So I'm going to wrap up, but I think I'm going to highlight the point that you all know, which is the goal of these things is to get people's inputs. So rather than just say, I'm not sure I agree with this, people should bring their arguments forward. Now, I am going to have to move on. So, Mr. D'Ambrosia, thank you for your contributions, and thank you for being on time.
You're welcome.
And so I will move on to my next slide. Oops. So our next presenter is a colleague of mine, is Rakesh Chopra from Cisco Systems. So Rakesh is a Cisco fellow, right, and he's been at Cisco for 23 years, so clearly he doesn't quite know when to leave. So I've actually worked with Rakesh for more than a decade. So Rakesh is doing a bunch of very high-level things with Cisco. One of his big things at the minute is really working on a project we call Silicon One, and it's really thinking about how to re-architect that high-end. So Rakesh has a lot of information on his LinkedIn page. I'd encourage you to go take a look. And Rakesh, could you take it away, please?
Sure, absolutely. Thank you so much, Peter. And thank you to Peter and the Ethernet Alliance for having me speak today. So today I wanted to sort of talk through about my view on what happens after 400 gig from a system vendor perspective, what it means to system vendors and what it means to our customers. So before getting into any of the details, I just sort of wanted to talk about the fundamental system architectures that I believe exist in the industry today. So we have a sort of standard fixed pizza box. These are sort of 1RU or 2RU devices with a single piece of switching silicon where all of the SerDes connect directly to the Ethernet ports on the front of the box. And depending on the actual signal integrity requirements, sometimes there's retimers in that system as well. The next is this type of system architecture that I like to call a centralized architecture. And really the big semantic here is that the switching silicon is on a different board than the front panel ports. And therefore we have a piece of active silicon on these sort of pluggable line cards on the front. And in cases we have redundancy built into the system where we use two different pieces of switching silicon. And finally, the third piece of system architecture that we use is sort of what I like to refer to as a big distributed modular system. So here we place multiple pieces of silicon on line cards connected to Ethernet ports, and about half of the bandwidth faces fabric cards, and we have multiple fabric element switches inside of the system. And because of the long signals that exist between the line card elements and the fabric elements, we typically need retimers on the larger versions of these chassis. Now, if you look at the type of SerDes which are used within the systems today, pretty much everything in the systems as we build them today is based on long-reach SerDes. And it's really only the optical modules themselves which use shorter reach SerDes towards the switching silicon in terms of trying to optimize that power footprint and help the cooling of those optics. Now, I tend to like to look at history to understand the trends that we've been going through and what that actually means to sort of where things are going in the future. So back in 2010, the sort of bleeding edge piece of silicon on the market was 640 gigs. It was built out of 64 SerDes lanes, each at 10 gig. And there was a QSFP plus form factor to bring that bandwidth to the front panel. 2 years later in 2012, the bandwidth increased to 1.28 terabits, and we did that by holding the SerDes speed the same at 10 gig, but doubling the number of SerDes to 128 lanes. 2 years again after that, in 2014, we doubled the bandwidth up to 3.2 terabits. We did that by holding the number of the SerDes the same, but increasing the SerDes speed from 10 gig to 28 gig, and introduced that sort of QSFP28 form factor. Again, 2 years later, like clockwork, we doubled the bandwidth again to 6.4 terabits. This was done by holding that SerDes speed the same at 28 gig, but doubling the number of SerDes to 256. 2 years later, again in 2018, the 12.8 terabit piece of silicon came to market. And we did this by holding the SerDes the same at 256 lanes around the device, but moving to a 56 gig PAM4 and introducing the QSFP DD56 form factor. Last year in 2020, the 25.6 terabit pieces of silicon came about. Now, what's interesting about this generation is actually different vendors have approached this problem differently. Some vendors got to 25.6 terabits by doubling the number of SerDes to 512 and using 56 gig SerDes. Other vendors kept the radix the same at 256 SerDes and doubled the bandwidth of the SerDes to 112 gig and introduced the QSFP DD800 form factor. And in 2022, my prediction is that we'll start to see 51.2 terabit systems in the market. And I think everybody here is getting there by holding the radix at 512 or doubling the radix to 512 and keeping the 112 gig SerDes around. So what's impressive about this is over 12 years, there's been 7 switch generations, increasing the bandwidth by over 80 times. There's been 4 SerDes speeds, moving the SerDes speed up by 10 times, and we've increased the radix of the switch 4 times for a total of an 8 times increase in the number of SerDes. So the big question I think that we need to answer is what's next? As we think about doubling the bandwidth from 51.2 terabits, how do we build a 102.4 terabit device, and how do we build systems around that? I think if we take another look at this sort of data and understand where sort of power has gone in all of these different systems, and we map that out over time, what we see is that although we've done a very good job of driving the bandwidth up, the power is endlessly increasing. And if we double click on that a little bit, what we actually see is that the SerDes, or that the core power in the ASIC, the digital logic, has increased in total power by 8 times over this 12-year period. The SerDes, on the other hand, over the same time period have increased by 25 times. Now, what you really see when you look at that data is the reality is that the analog portion of the SerDes isn't keeping up with the sort of technology node advancements that we get within silicon. And so we're seeing a very strong increase of SerDes power over time. In that same time frame, what we see is the optics, which is really a combination of the front-end optics and the host-facing SerDes, has increased by a whopping 26 times. And to cool all of that additional heat that has been generated by these components, we've had to increase the fan power by 11 times in the system. So over this time period, although we've gotten our systems much more efficient, we've actually increased the total power draw of our systems by over 22 times. Now, I think at the end of the day, why am I focusing on power so much? It's because, as John Aaron likes to say, power is everything. It fundamentally limits what we can build as a system manufacturer. It limits what our customers can deploy. And I think most importantly, frankly, it limits what our planet can sustain. And I think we as an industry really need to get behind this notion that we're going to adopt a sort of power-first design and deployment methodology. And this is quite a change for us as an industry, but one that I think we need to really consider adopting. Now, as we start to think about that power draw, we have to start to think about how do we actually begin to address it. And if we look back at where the power was being consumed in that 51.2 terabit generation, what we see is a large portion of the power is actually consumed by the SerDes. And those are actually the things which are not scaling linearly with technology. And so we have to attack this sort of head on. If you double click a little bit more, what you start to actually see is that there's a strong relationship between SerDes power draw, the rate and the distance that you need to drive these signals. And so if you think about what that actually means, if we take an architectural approach to trying to solve power and we bring the optics and the silicon closer together, we can actually change the slope of that power draw from generation after generation. And this is why I actually think this notion of co-packaged optics is an inevitable outcome for the industry. But it's not only power. Again, I think if we look back at history and trying to sort of use history again as a predictor of the future, what you see is that when the communication industry was first created, all interconnect in the industry was copper. But as data rates have increased, what we started to see is that the longest distance connections switched from copper to optical first. And today we're in a generation where basically everything outside of the rack is done from optics and everything within the rack is done in copper. But data rates really aren't slowing down. And so I believe this is actually an inevitable transition. And if you ask my opinion, I think in the 51.2 terabit generation, it's when we'll see this notion of co-packaged optics come to the market. But I do believe that we'll still have this sort of notion of pluggable form factor optics in the 51.2 terabit and probably generations after that as well. Now, the one thing to sort of realize here is that power optimization is not just about what happens within the system. It's also how networks are built, and these can play a very significant role in thinking about the total efficiency. So if you think about a data center, the main incentive of a data center is to get as many servers into the data center as possible because those are what generate revenue into the system. Now, if you think about how to do that, there's really two fundamental ways to do it. The first is what I would consider scaling out the architecture, and that's really shown by, on the x-axis of this graph, by adding larger and larger switch radixes. The other way to do it is what I like to refer to as scaling up, which is really adding additional layers in the network, which is shown as unique lines within this graph. Now, if we double click on this data set a little bit, what we actually see is that unfortunately, in reality, there is no free lunch. So as we think about scaling out or doubling the radix, what we find is that depending on the number of networks and the number of layers in the network, you can get between 2 times and 16 times more servers in the network. But unfortunately, as you do that, we introduce a much more complicated cabling infrastructure into the infrastructure. But there's a more nuanced side effect. If you hold the bandwidth of the switch the same and scale the radix, what you end up doing is you end up dropping the Ethernet speed. And that creates a worse ECMP hashing and therefore ultimately a lower link utilization in the network. The other way to sort of do this is sort of scale up. And this is, again, adding network layers into the infrastructure. By adding a layer, depending on the exact radix of your network topology, you can add between 2 times and 256 times more servers for each one of these layers that you add. But unfortunately, as you add layers to the network, it ends up consuming more power per server for your network infrastructure, and so you get a less efficient network from a power perspective. But if we want to just sort of think about it in a slightly different way and make the conversation easier, if we think about the positives of each one of these architectures, it helps a little bit. So by doubling the radix or scaling out horizontally, you drive and optimize power efficiency. Where if you scale up your network, you end up sort of optimizing the link efficiency of the network. Now, most web-scale customers, again, have sort of settled on this notion of using about 100,000 servers from a target perspective in terms of what you can end up building. And many customers have adopted either a radix of 32 or 128 in their infrastructure. And so if you look at this graph, you can see that you need a 4-tier network with a radix of 32. But what I actually like to think about is I like to actually overlay the switch bandwidth discussions that we just had with the network radix and try and understand what that means. And if you look at the sort of radix of 32, what you actually end up seeing is that the 12.8 terabit generation, where we used 400 gig E with a radix of 32, might end up being the last real-world deployment of sort of a radix of 32, because the Ethernet rates from an Ethernet MAC perspective, as well as the number of SerDes necessary in the optics, really just aren't keeping up with that. And so I think the question here is whether customers are going to start migrating from a radix of 32 to a sort of a radix of 64. Now, if they do adopt a radix of 64, what you actually see in sort of this next generation interface is that for an 800 gig E, using 8 lanes of 112 gig SerDes for the 51.2 terabit generation seems like a pretty good fit. And similarly, in the 102.4 terabit generation, we'd be looking at a 1.6 terabit Ethernet with 8 lanes of 224 gig SerDes. For the customers who end up using a radix of 128, and there's many of these in the industry today, I think what we see here is that there's really a clear need for an 800 gig E defined with 4 lanes of 224 gig SerDes. And the other nice thing about the sort of radix of 128 is you can actually see that there's a runway here before we end up running out of the number of lanes for pluggable optics. And that gives us a bit of runway here from an Ethernet MAC and an optics form factor definition. Now, if we take a step back again and sort of come back to look at the system-based architectures, and we think about what happens with a sort of 224 gig transition, what I would contend if we adopt a power-first methodology is that we must define the standards for 224 gigs such that we can build systems with absolutely no retimers between the switch silicon and the front panel optics. And I would also contend that the switch silicon, we've really got to move away from the notion of using long-range SerDes within our systems and focus on using VSR SerDes towards the front panel optics, and really consider the 112 gig generation as the last major generation for passive copper cables. Now, I do agree that there are going to be customers who want to have shorter reach copper cables, and so here my proposition would be that we use active electrical cables as opposed to passive copper cables. Now, this doesn't remove the restriction or the requirement that we need long-range or medium-range SerDes. I think within the system, we'll still consume MR and LR-based SerDes for those chip-to-chip style interconnects within the systems. As we think about 224 gig from a CPO perspective, really my contention is that we'll really focus that on the client-side optics. We'll move those launching directly out of the switches. This will really be the second generation of CPO, and so we'll get quite good market traction. But I still think that the rest of the system here will remain primarily an electrical interconnect. But looking forward into the future, obviously, at some point, this transition of using optical, even within the system, is going to happen. It's really just a question of when rather than if. So sort of coming all back up and just thinking about where we are, I think ultimately at the end of the day, the pace of bandwidth growth and innovation really isn't slowing down. The reality is that this is really driving a few basic key points. First, that power is growing at an unsustainable rate. Second, to help manage this, co-packaged optics will be realized in the 51.2 terabit generation. And to continue the bandwidth growth beyond that, we really must focus on this definition of 224 gig that you heard about earlier from John. I think we've got a clear need for 800 gig E with 224 gig SerDes to align to the customers who need a radix of 128. And I think there's also potential here for the definition of 1.6 terabit via 224 gig SerDes as a sort of follow-on project. But time is of the essence here. So we talked about earlier, or John talked about earlier, about sort of a 5-year notion for the definition of these things. We've really got to get going, but we've got to be very careful that we do this well. And I think, to be honest, at the end of the day, I think we're really at an inflection point from an industry perspective. Right? I think power drives, again, what we can build, what can be deployed, and what our planet can sustain. And this is really creating this fascinating view of a business, a technology, and a moral imperative for the first time in the industry. And the confluence of these three events, I think, gives us the ability to drive a fundamental new set of innovations behind trying to sort of bring these next generation technologies to the industry. And for myself, I guess I'm super excited about the potential of all of this, because as an engineer, seeing all of these things come together and help shape what we do in the future is really very exciting. So with that, Peter, I'll pass it back to you, and thank you for your time.
So Rakesh, that was sort of awesome. It was not only good, it was also on time, so I will congratulate for that. So I've got a couple of remarks and also a couple of questions. So it is the first time I actually heard morality brought up in a technology presentation. And I think it's good for us to remember the impact that we have on the rest of the world. I'm a little curious as to how you came to this conversation of focusing on this morality as opposed to technology.
So I think it's actually not just focusing on morality. I think it's actually focusing on all three, i.e., because power now just fundamentally limits the type of systems that we can build, we have to solve it from a technology perspective as an equipment vendor. Because it's limiting what our customers can actually deploy in their data centers, right? Our customers are out of power in their facilities. So every watt we consume in networking means that they can't consume a watt in servers. And so we've got to get to the point where we are sort of really doubling down on driving that power down. Now, I think the morality piece, I think, is a fascinating new sort of piece of that puzzle, which is at the end of the day, again, this might be my personal opinion here, but we really have sort of one planet to live on. And I think because the things that we work on today are so prevalent in the industry, I think it actually gives us a great lever as an industry to sort of try and change that trajectory. And then I think the other piece of it is because power costs our customers so much money, and some of our customers are sort of adopting green initiatives themselves, there's a double whammy for them, which is not only is it expensive for them to deploy, but they have to offset that carbon somewhere else. And so again, I think this whole notion of morality is starting to filter into the discussion unlike before. And again, because you've got all three of those things going together, I just think it's a fascinating time to be an engineer.
All right, so we have a couple other questions I'm going to combine together a little bit. So there was a question about, it's all about if power per bit doesn't improve, what do you do next? And I think what you said is, well, it has to improve.
Yeah, I think that's right. I think, to be honest, power per bit has actually always been improving. So if you look at the data, it's not that the power per bit has not gotten better over time, right? In the end, we've increased the bandwidth by 80 times, but we've only increased the power by 22 times. So our power efficiency is getting better. My contention is that we actually have to change the slope so that we are doubling our bandwidth with a very small power increase.
Is there a slide that would help us talk to this particular one? Is there one of the slides that would help us talk to that particular one?
Sure. So let me go back to this slide here, if I can figure that one out. Does this come up? Yeah. So again, over the time frame, we've increased the bandwidth by 80 times, which is, again, an amazing accomplishment. And over that time frame, if we sort of animate this out a little bit here, again, the total power draw increase here is 22 times. So the power per bit actually has done a pretty good job of improving. My contention is it's just not enough, that we've got to grapple with this endless power increase generation after generation and really take that as the high order bit for when we make trade-offs. Because we all know that in engineering, everything is a trade-off. You can't have one thing without impacting another thing. And I just think that now power has sort of elevated, in my perspective, to the fundamental thing that we need to address as an industry.
So maybe sort of digging into that one a little bit more. There is the power per bit, but I think what you're talking about is effectively the power density of a system and how it limits your ability. So it doesn't really matter. We all want to get more stuff in a small place, and the ability to cool those things is becoming not credible. I mean, do you have any impressions on the impact of that from the big data center guys?
Yeah, I mean, I think there's several aspects to that, Peter. It's a great view that you mentioned there. So I think data centers used to be limited by the size of the equipment that they would deploy. I actually think for the last several generations that hasn't been true anymore. I think the fundamental limitation for data centers is about the power per rack, the power per row, and the power per building. And so the thing which limits it is no longer how small you can crunch your equipment, it's how efficient is that final equipment. And so actually, I wouldn't be surprised if we actually see sort of an expansion of equipment size in order to sort of drive that efficiency vector moving forward. But And the flip side is actually, if you remember that, what I commented about the relationship between distance and power efficiency, there is actually an inherent advantage in cramming things together. So you've got these two effects of wanting to cram things together to make them more power efficient, but also wanting to spread them out to be able to sort of cool them more efficiently, fighting against each other endlessly.
Okay, so I have another question here I'm going to try and get right. And the question says 51.2T is early for CPO because the 128 by 400 gig is okay for conventional modular. And I think this really goes back to when does co-packaged optics go from being interesting to being really needed?
Yeah, it's a great question. It's a great question. So I think it's clear at this point that building what I would call a traditional system architecture with 51.2 terabits with standard pluggable optics is absolutely possible to do. And I think you will see vendors and customers consuming that style architecture. I think there's two reasons to sort of make CPO happen in that generation. The first is around efficiency. I think if you run through all of the math, at the end of the day, you'll find that you'll get a better power per bit for a CPO versus a traditional pluggable optics. But I think the second one is actually more important, which is I think anybody who claims that building a CPO-based architecture or co-package-based architecture is an easy thing to build is probably missing the complexities that show up. And so we actually, as an industry, we want to make sure that we're embarking on this transition before it is what I would call a fundamental requirement, before we've driven off the cliff that you can't build a traditional system architecture. And that complexity is true both from how equipment manufacturers build equipment or how ASIC or optics manufacturer build those devices, but also how the customers deploy it. What does it mean to a data center customer to be able to lose this notion of pluggability from a failure rate, from a management, from an ecosystem perspective? There's many sort of impacts associated with co-packaged optics that as an industry we've got to sort of flush through and get right before it's too late.
Okay, so I'm going to hit you for one more. And I think you've covered a bunch of this already. Really, I think the meta question is, with the combination of reaches and radix and everything else,
yeah,
does the traditional design that we're designing today in terms of how the network is laid out, does that stay or does that morph? And do we know what that looks like?
Yeah, it's a great question. I mean, I think I sort of hinted a little bit about this with the sort of radix of 32 going to radix of 64. I think when you double click on the data, what you really see is the bandwidth growth, and John commented on this as well, the bandwidth growth that you see within these sort of hyperscaler or web scale data centers far exceeds what we're doing from an industry perspective in terms of Ethernet MAC rate adoptions. And so when you think about what that really means, it means the radix of these networks is continuing to grow and grow and grow and grow, or you're going up in topology. And you know, again, I suspect that because power is I believe the fundamental limiting factor, people have a tendency to try and scale to the right. But the challenge that exists there, as I mentioned before, is
when you say scale to the right, what do you mean? Do you mean higher radix, more power per lane?
Yeah, scale out style architecture. So from going from a by 32 to a by 64, by 128, or even up to a by 512 based radix. I think there's going to be a tendency to do that. But I think one of the challenges that exists there is if you think about sort of a 51.2 terabit device with a radix of 512 by 100 gig E, that works okay if your servers attaching into your network are 25 gig servers. But what happens when those servers become 100 gig, or you have AI-based compute, which is plugging in at N by 400 gig? So you've got this endless push between scaling out and scaling up. And I think it's something that will be interesting to see how it plays out over time.
All right, so we do have more questions, but I am going to have to move on. So I will thank you for an excellent presentation and possibly even more excellent questioning. And what we'll probably do is we'll probably push the other questions to you later on. I would ask, again, for all the people I didn't accent enough, submit your questions into the Q&A. We'll pick up and synthesize the ones we can, and we'll figure out a way to get back to you otherwise. Also, there's a note, we will get these slides will get shared. And with that, Rakesh, I would thank you for showing up. And I'm going to move on to our next presenter.
Thanks for having me.
So again, thank you for your time. Okay, So we've heard from John, and he's really given us partly from the standards, partly what he's seeing. And now we've heard from Rakesh, and Rakesh was giving, what he sees talking to Cisco's customers and what he thinks is technically possible. So now we're going to have a panel debate, right? And so this is what we're seeing from the market information. So our panelists today, we have Sameh. I'm not going to work on her second name because I would probably butcher it. So Sameh is a senior director at Dell'Oro Group. She's been with the firm for 10 years, and she really covers the switching market. And so her individual section is market drivers for next-gen Ethernet speed. We have Dave Ofelt from Juniper Networks. So Dave is a guy I know pretty well from being at IEEE 802.3. He's a pretty humble guy. He's been with Juniper for more than 20 years, but his LinkedIn page describes him as a grunt engineer, which I think is a little bit underselling himself. And he's also active in .3 and OAF. We also have Vlad Kozlov from LightCounting. And so Vlad is the founder and CEO of LightCounting. And he really LightCounting looks at optical networking, all the components, right? Data shipments of high optical interconnects and Ethernet transceivers. So as I said, that's our panel today. If I skip on, our first panelist to speak is Sameh. So Sameh, are you with us?
Yes, I am. Can you hear me, Peter?
I can hear you. I cannot see you yet.
Do you want to see me, or do you want me to keep the camera off during the...
If possible, seeing I find is helpful, but it's really up to your comfort.
Yeah, I can turn on my camera. 1 second. Can you hear me?
Excellent.
Can you see me now? Perfect.
You can.
Awesome. Hi, everyone, and thanks, Peter, for the introduction. I'm going to read my last name so that next time we'll practice it. We'll make sure to practice it together, Peter. So I'm Sameh Boujelbene with Dell'Oro Group. Dell'Oro Group has been in the market research business for 25 years, and we cover all those areas. I personally track switching, that's data center, as well as campus switching. But of course, today I'm going to focus more on the data center side of the market. Today I'm going to present on the market drivers for next generation Ethernet speeds on data center switches. And these are the topics, the main topics that I'm trying to cover during my presentation today. So I'm trying to, first I will try to provide an update on speed migration by the various market segments. Then I will provide an update on the 100 gig upgrade cycle and how the 100 gig migration has unfolded. Next, I will provide an update on the 400 gig upgrade cycle and what are the major constraints that the industry is facing for the 400 gig migration. Next, I will discuss the need for 800 gig and why we need 800 gig before we go to 1.6. And lastly, I will leave you with some thoughts about the major constraints for speeds beyond 400 gig. Rakesh did an amazing job really touching on all those all the major constraints, but I will reiterate also my opinion there. With that, let's start on this chart. So this chart basically looks at the different segments driving the market. It looks at revenue, but we are seeing the same trends and market shifts also obviously happening in terms of ports, right? So the main point here is that the last decade of networking has been dominated by on-premise type of enterprise data centers. These are data centers that are relatively small in size, i.e. hosting a few thousands or at most tens of thousands of servers. Whereas if you look at the next decade, we expect the networking market to be driven by cloud service providers, which are much larger in size. And when we say much larger in size, these are data centers hosting hundreds of thousands of servers, as Rakesh alluded to earlier. And by the way, this shift from on-premise type of enterprise data centers to public cloud has been further accelerated by the pandemic. So why does it matter to look at the market in these different market segments? It matters because these various market segments migrate to different speeds at different times and using different topologies. The difference in timing is due to bandwidth requirements, as well as the length of refresh cycles, which we estimate to be around 3 to 4 years in the cloud versus 5 to 6 years in the enterprise. So let's look at how fast each one of these market segments is migrating to higher speeds. So before I start doing that, and before I talk about the speed migration by market segment, I wanted to revisit very quickly the roadmap of the SerDes speeds, because as you all know, SerDes lanes are the building blocks of network speeds. And the point here is that each SerDes technology will drive new speeds as well as new waves of existing speeds. For example, with 100 gig, we had the early or the first generation or the first wave being based on 4 lanes of 25. The next gen will be based on 2 lanes of 50, and the third generation will be based on 1 lane of 100 gig. And in each wave of these speeds and each generation of these speeds will be adopted by different market segments at different times and for different purposes and deployment scenarios. Okay, so let's look at, for example, 100 gig. Okay, so this chart looks at 100 gig deployment by market segment. And you can see that the vast majority of 100 gig shipments for the first 2 to 3 years have been driven by cloud service providers. And those were really mostly the 100 gig based on 4 lanes of 25. And they've been deployed by the hyperscalers from top of rack all the way to leaf and spine. Okay, if you look at large enterprises, it took them about 3 years to start adopting 100 gig switches. So enterprises were lagging cloud service providers in terms of their 100 gig adoption. And not only that, a big portion of the early 100 gig switch port deployments by these enterprises were actually running 40 gig optics, not 100 gig optics. So what happened is that enterprises were buying 100 gig switches instead of 40 gig because they were basically priced the same. However, the optics are a different story. So 100 gig optics were still expensive. And since enterprises did not need the bandwidth at the time, they were just running the 100 gig switch ports at 40 gig speed until 100 gig optics came down in prices. So based on that, when I get the question whether enterprises would need more than 100 gig speed over the next 4 or 5 years, my answer is not really. They will not be needing more than 100 gig over the next 4 to 5 years. So let's look, for example, at 400 gig, and I will show you that enterprises will not be a major contributor for 400 gig. So as I mentioned, the first point when you look at this chart, which looks at 400 gig shipments by market segment, you can see that the adoption from enterprises will be very slow during this time horizon. Again, the main reason is that they don't need more than 100 gig of bandwidth, and 400 gig is priced at least twice the price of 100 gig on the switch, not even including optics. And so if you don't need the bandwidth, you don't want to really pay that price premium. But we think that as we get to next waves of 400 gig speeds based on fewer number of lanes, then the cost will come down, and then we will see adoption outside of just the hyperscalers, right? But for now, since the 400 gig adoption is driven by the hyperscalers, let's double click and see how the hyperscalers adoption of 400 gig has been unfolding so far. Okay, so if you look at the early adopters here on this chart, so you can see Google was the first to migrate to 400 gig. That was back in 4Q18. That's when it started. Few really small quantities, but that's when it started. And the reason Google was able to start deploying 400 gig that early is because they elected to go with 2 by 200 gig optics, which had an earlier time to market. But obviously, we report those ports under our 400 gig segment. I can't really clarify that point enough because I've been getting a lot of questions around it. But yes, we do report them under 400 gig, although they are 2 by 200, but we really track the speed on the switch ports, not the optics, okay? The next cloud service provider that was able to catch or to adopt 400 gig is Amazon. So Amazon's deployment of 400 gig started by end of 2019, which was a little bit delayed because they had some issues with optics, but finally at the end of 2019 they were able to start the 400 gig deployment. And what's interesting on this chart is that you don't see Microsoft until 3 years after initial 400 gig deployments, right? So Microsoft are really late adopters in this cycle. They haven't started the 400 gig. They are expected to start hopefully by second half of this year, and there are a few reasons why they are a little bit or their adoption is a little bit delayed. First challenge is availability of 400 gig ZR optics for DCI, but the second and more important challenge is power consumption. Power. I couldn't agree more on Rakesh's point there. So Microsoft, for example, they really needed, they are power constrained. They needed to wait for next generation chips from Broadcom, like basically the Jericho to C+, with lower power consumption. And that's what is really delaying their adoption. And what that effectively means is that Microsoft is deploying the technology about 3 years after availability. 3 years, and I believe that, I mean, as I mentioned, power is really the main constraint there, is one of the main constraints, right? So, and the last point on this chart, obviously, if you look at this chart, you don't see Facebook. That's because Facebook is on the 200 gig path before they go to 400 gig, and I will explain why they adopted 200 gig before they will adopt 400 gig on the next chart. Okay, but really the point that I'm trying to make on this slide is that we not only have a divergence in the needs of cloud and enterprise customers, but even within the top 4 cloud service providers, there is divergence in the timing and the choice of the various speed implementations. So that's really key when you think about future speed on data center switching. Don't expect to see the mass adoption that we saw with 100 gig, where most of the hyperscalers moved uniformly to 100 gig. I believe that moving on, looking at new generation of our next generation of Ethernet speeds, we'll see divergence in need, divergence in implementations, and we will see staggered type of adoption, and not really mass adoption from hyperscalers from in the early stage of adoption. And this point will be further illustrated on the next chart. So on the next chart here, this chart is a little bit detailed, but it really helps to understand why or what each of the hyperscalers is using, and the different implementation that they are choosing depending on their architectural choices, right? So you have the timeline. That's the timeline of switch availability, not really the timeline of deployments. And then you have the different chip generation, and then the different electrical I/O speeds that are driving the different chip generations. And I try to portray what each one of the hyperscalers is going to deploy as a configuration or as an implementation for each chip generation, right? So if you look at Google, they are currently using 12.8 T chip to fan out about 32 ports of 400 gig. Obviously, each port, as I mentioned, is configured as 2x200. Next, they will be deploying, or we expect them to deploy 25.6 T based on 100 gig SerDes to do, again, 32 ports of 800 gig, but each port will be configured as 2x400. So basically, the 100 gig SerDes will allow them to build high-density 400 gig systems and to match the electrical lanes with the optical lanes. So that's really the goal there. And what that means that the early 800 gig deployment here, it's not actually going to need 800 gig MAC. So we need 800 gig speed, or the industry needs 800 gig speed, but at this time frame, the industry did not necessarily need 800 gig MAC for the 25.6 T chip generation. That's really for 25.6 T. But where I think the 800 gig MAC may make more sense is when we move to 51.2 chip, as I'm alluding here on this chart, because that's what allow us to keep basically the same radix. But again, as Rakesh said, it's going to be so hard to keep 32 ports on 1U. I think we're going to move to 2U at that point in time. Okay, so that's Google. A lot of details there, but hopefully we're able to follow the logic. If you move to Amazon, they are very similar to Google in terms of choice of chip generation. However, the configuration or the implementation is a little bit different. The 400 gig is implemented or used as 4 by 100, and the 800 is used as 8 by, or will be used as 8 by 100. Again, initial 800 gig speed implementation at Amazon and Google did not or will not require 800 gig MAC. Okay. The third hyperscaler here on this chart is Microsoft. As I mentioned, they are really behind in terms of the 400 gig migration. I'm not sure if they are considering 800 gig at this point, but even if they would consider 800 gig as the speed following 400 gig, that will require some changes in their network infrastructure because of power. Again, power. So even if they any speed beyond 400 gig, to my understanding, it will require some changes in topology at Microsoft. And the last hyperscaler on this chart is Facebook. And Facebook is on a different path. As I mentioned, they will move to 200 gig before they move to 400 gig. And the main reason is because they want to keep a radix of 128. So depending on the chip capacity, they will be able to find out either 100 gig or 200 gig or 400 gig. So you can say that Facebook, in terms of port speed requirement here, they are a little bit behind the other hyperscalers. So I think this chart is a lot of details, but I think the point here is that there is really a divergence in the need and requirement and timeline across the different hyperscalers. All right, so let me move to my final chart here, and I want to really conclude my discussion with some thoughts around the major considerations for next Ethernet speeds. So the first point here is that 100 gig SerDes chip with 100 gig lambda will start shipping in 2021, or start ramping at the end of 2021 with volume mostly in 2022, and they will drive 800 gig switch port deployments. But keep in mind that those initial 800 gig switch port speed deployments do not require 800 gig MAC. The second point is that 200 gig SerDes are needed for 1.6T, but the availability of 200 gig lambda may lag, given that connecting 200 gig SerDes to 100 gig lambda would require gearboxes, which add complexity. We expect that 100 gig SerDes with 100 gig lambda will be the main building blocks for speeds beyond 400 gig in the next 4 to 5 years, in the foreseeable future. Main reason there is time to market. If you don't have the ecosystem around 200 gig ready, i.e. on the electrical side, as well as on the optical side, then your best bet is to use the existing building blocks, which are 100 gig SerDes and 100 gig lambda. The third point is power is one of the major constraints, if actually, as Rakesh said, probably is the major constraint as we move to speeds beyond 400 gig. And we believe that future data center networks may require a combination of photonic innovation or co-packaged optic, as well as some kind of optimized network architecture to accommodate higher network speeds. When I say optimized network architecture, it includes everything from trying to remove tiers, adding tiers. So there are a lot of area for innovation there. And what that means is that this will create a big lag between the timing of technology availability, or what I mean there is really the availability of the different building blocks of the technology and volume adoption, even at the hyperscaler. So I expect moving forward that even if we have the building blocks ready, how you put them, how you implement them in the network will take really longer time. So that's from a market perspective, because we care about, forecasting the different volume in the market. But obviously from a standard perspective, that's not to say that we have to start now. So absolutely we have to start yesterday. So thank you. So that's all from my side, Peter, and I will hand it over back to you.
So thank you, Sameh. I have to confess, I'm still not brave enough to try your last name at this stage, but I'll work on it in the future.
No worries.
I say, folks, what we're going to do is we're going to have a joint Q&A session at the end. So right now we are on to our next presenter. So this is Mr. Ofelt from Juniper Networks. Dave, are you ready to go? He tap dances quietly while waiting for Mr. Ofelt. Mr. Ofelt, I cannot see you, and you're on, and I cannot hear you.
Can you hear me now?
I can hear you now.
Okay. When I try turning on my camera, it seems to turn everything off.
then let's just go with the sound for the time being.
And spare you the sight of me. I'll try to figure it out for the panel questions.
Thank you. Okay.
So I am in a position where I know I'm speaking after John, who would have covered, the beyond 400 gig status and what we're thinking about and what we might be doing there. Coming after Rakesh, who is, always gives really good views on the system implications and the roadmaps there. And I'm sandwiched between two analysts who are actually giving you the graphs and details you want. So I'm going to try to say some intelligent things, but forgive me if I'm I'm not as interesting as the rest. So I just want to talk some about this, where we are right now, looking forward at doing something after 400 gig. And one of the things when we're at this stage of 400 gig, we sort of look back at the 100 gig generation. What changed in the world between starting 100 gig E and actually finishing the project? And we noticed there are little things like, Netflix went from mailing CDs to being 30% of the internet bandwidth. Facebook went from, like 10,000 users to 1 billion users. And so it was a big, big change in how the network looked and what it was used for. When I look back at 400 gig, it's less, the applications are just more and more and more of the same. But what has actually changed, I think, a lot is who is driving what we're doing and the standards in the industry for the technology. When we started 400 gig, the carriers really drove the agenda. The same thing as 100 gig and before that. They were the ones wanting faster. They were wanting new interface rates, and they're really giving their needs, and we tried to meet them as much as possible. One of the interesting things about this is going faster was actually an interesting thing for them to do, and they were willing to sacrifice, faceplate density, cost per bit, and power per bit to get this faster rate. It was worth something for them. Now, flash forward, N years later, when we finished 400 gig E, the carriers really weren't driving the agenda anymore. Everything's been replaced by the hyperscalers, and the rest of the world seems to be fairly content to get the leadings from where they're driving things. And this new world, the end users are not willing to sacrifice just to get a faster rate. We as an industry built, CFP8 based 400 gig E. It's lower density than the QSFP or QSFP-DD OSFP type solutions, and it didn't catch on because no one was willing to ship something that was going to compromise density. Now, it's been exceedingly useful from a tester standpoint, so we can actually, as vendors, build these machines and get them into customers' hands. But as an actual form factor, it wasn't very interesting. And Sameh covered a lot of this, but customers are waiting to deploy 400 gig until it sort of has the right color or the right flavor for them. It has the right, it's going to be parity with power cost density as dense 100 gig E, because that's really the commodity rate. And most people are using a lot of 100 gig E and then maybe some other rates. Some users really like to view their routers as just a box with a bunch of holes in the front of a given rate. And exactly from hole to hole, they'll make a decision to plug in, different optics or different interface types based on the exact needs of that port. And so maybe it's a router sitting in a part of the network where it has down-facing ports to the TORs. They're going to be multi-mode fiber. The uplinks at that point are 2 kilometer single mode. But the same type of routers using higher up in the network, its downlinks now are 10-kilometer links, and its uplinks are, possibly something like 400 ZR. And that's a really nice vision. But the problem is, until you get everything, you can't deploy anything. And so some vendors are waiting until they have all of the interface types they need. And then it seems like some other users are waiting until a long-lived on-the-wire interface happens. And so we did some 50 gigabit per second based optics. And it seems like a lot of end users are just waiting until they get the 100 gig per lambda optics before deploying. And they've got really good equipment in the meantime. They can just continue deploying it, and they wait until all of the facets are right before they ship. So I think, looking at this little bit of history, and I'll talk more about this, I don't think things looking forward now in post 400 gig are going to be substantially different in expectation. And so I think people will be looking for parity in cost, power, density, and packaging, and the same kind of diversity in median reaches. And also, they may be waiting until they get the right collection of those before they have to deploy. Okay, so now why might we want a faster rate? I think there's two basic reasons. One of them is we just want to go faster, and the other one is there's some other stuff that in the end may be more important. So the faster bit, and I think Rakesh and crew have mentioned this, is it's possible to bond together lower rate interfaces to make a faster link. We did a silly picture as part of the 400 gig call for interest where we tried to build up 100 gig E from 1 gig E's, and we have this bundle of 80 cables, and it looks ridiculous, and it was kind of fun to do. But at some point, bonding together slower interfaces, you either get too many of them, which is just cumbersome, or you end up with statistical behavior that is either traffic dependent, or you're not utilizing, or you're not willing to utilize the full rate of the interface. And so people throw around about an 80% utilization for lag, and that's actually quite a bit of port bandwidth wasted. And so eventually, people will want to move to a faster MAC rate. It's going to be incredibly personal when they do that. And it's going to vary from user to user. And some people are more worried about this than others. Now, there is a place where you go faster, and this is, I think, more of the traditional carrier reason, is if your fiber is expensive or scarce, then faster rates allows you to get more from your existing resources. And that can be really important. A lot of the hyperscaler deployments can be more fiber rich than others. Either they control their own plant, or they have different assumptions on what their fiber looks like. But it still is a thing. There's going to be some places in the network where going faster allows you to use an even more expensive resource more efficiently. So now, what are the other things? The projects where we develop faster interfaces frequently build other useful building blocks. And so for 400 gig E, we ended up building 50 gigabit per second chip to module interfaces. And we also built 100 gigabit per second wavelength optics. Now, here we took a very specific one of them. It was parallel single mode at 500 meters, which was a new reach at the time. And there was a lot of doubt in the industry about when 100 gig per lambda optics were practical. And there were good arguments why this, the 500 meter 100 gig reach was achievable, and it allowed us to prove it out. And we followed that up with a bunch of other projects to flesh out the 100 gig generation. Now, these building blocks, the most important thing they did was allowed commoditization of the slower rates. And so the technology built in 400 gig E allowed us to build 50 gig E, which is going to be a popular rate, single wavelength 100 gig E, which is now a long-lived on-the-wire interface for 100 gig E, and allow us to build denser modules. And so, we have this new faster rate available, 400 gig E, but what it really allows us to do is build things that we need to ship in the many, many, many millions now for the sort of the commodity interface, build those cheaper, denser, and better. And these are going to be the sort of the high volume commodity interfaces for the near future. So now, beyond 400 gig E, we are going to have to go faster. At some point, each end user will find it worthwhile to move faster rates. Sameh has a great slide showing just a couple customers and how different they are about making this decision. And the time frame from us starting this new rate project to having high volume availability with suitable packaging and system support, it's going to take many, many years if we actually do something worth building. And just as an aside, this isn't a standards are slow thing. You can build a lot of this stuff pretty quickly as long as you need to build in very small quantities for a single customer or just for yourself. But I think one of the things that we do in IEEE, and where we're doing this work really, really well, is building an ecosystem that allows us to build this stuff at scale and head towards commoditization. And that's a really, really hard problem. It takes a lot of different disciplines in order to come together and solve this. And it just takes a long time. And we're working with really sort of very hard technology. To go faster, we usually have to harvest margin or get fancier. To harvest margin, we have to be more and more careful with our analysis and testing techniques. To harvest or to do more clever things, it takes a lot more engineering to prove to ourselves that we get it right and to get the right thing. And these just take time. It doesn't seem that there is an significant industry demand for a faster MAC rate right now than 400 gig E. Some people talk about it, some people say they want it, but it's not clear that the demand is large enough that it's going to drive an entire effort. And so I think this allows us to focus on longer term, look at goals that allow us to build sort of very useful building blocks and pick our technology accordingly. If you do need a faster MAC rate, the Ethernet Technology Consortium has an 800 gig E, and it's there for faster MAC rate. Now, it's not going to give you cost per bit, density per bit, or power per bit that's any better than just gluing together two 400 gig E's, because that's all it is. And so to improve on all those things, we actually need to look at new technology. Now, whether we do 800 gig E or 1.6, I think those are likely choices because this sort of power of two or factor of two, factor of four interface growth really fits in the patterns we've been doing for quite a while and allows us to do forwards and backwards compatibility quite smoothly. Those two are the likely choices. I have worries that 1.6, and that should be terabit Ethernet, not 1.6 gigabit Ethernet. That's kind of slow. 1.6 terabit Ethernet, we can build it. And as an industry, I know we can build the chips. I know we can build all the pieces. We can ship it. I'm afraid that its broad market potential is going to be lower because it'll be too clunky. You're going to have to give up on power per bit or cost per bit or density so significantly that it may not be actually interesting to anybody in the end. As we go through the study group and task force for John's new project, we'll see how this shapes up. There's going to be a lot of opinions on this, and I'm really looking forward to hearing them. Now, the other stuff is the building blocks for beyond 400 gig E are almost certainly going to provide the tools to commoditize 400 gig and 200 gig E. And this is key because as this project goes on, we'll need something to take over from the current 50 gig E and 100 gig E. And we roll forward, and so the whole set of interface speeds will ratchet up. And I think both 800 gig E and 1.6 terabit Ethernet will provide excellent building blocks for this. Now, last thought, I call it caveat, but it's more just something to think about, is it's getting really harder to go faster. And it's an open question whether we can build systems supporting the next rate and higher densities the way we're currently used to. Rakesh alluded to a lot of this, but it's if we want to build a box that has, a scalable line card based system with pluggable modules on the front, it may be that we can do that, but it is so expensive to build the boards because we need, excellent media to do electrical signaling over, or it's using exotic interconnect from packages to the front panel that are going to work eventually, but turn out to be harder to manufacture or less reliable or just more expensive in the near term. And it's going to be, it's not clear right now whether we continue building things that we've been building and that's going to be actually acceptable to the end user. It's also not clear that any of the alternate systems that people are proposing are going to be acceptable yet. And so we're in this really interesting, scary point where, we're pretty sure we have to change some stuff. Everybody's pretty sure they'd really rather not change it if they don't have to. And when that trade-off becomes the right thing to do is going to be, it's not clear to me yet. And I think Rakesh, addressed this quite well, but I think if you ask every member of our community, you'll get a slightly different answer on what's acceptable, what's not acceptable. And many of the people will think that their needs are obvious, and will be shocked to find out that they differ from everybody else's. And so this is what we're going to have to navigate over the next year or so as we decide what is next after 400 gig E. So that's all I have to say today. And hopefully people will have some good questions later. Thanks.
So thank you, Mr. Ofelt. I do appreciate that point of view. So as I said earlier, guys, we are going to have a joint panel Q&A at the end. So feel free to drop your questions into the Q&A tool. And now we have to move on. And our next speaker is Vlad Kozlov from LightCounting. Vlad, are you ready to go?
Yes. Can you hear me okay, Peter?
I can hear you okay.
All right, perfect. Let me turn on my camera, see if that works.
And now I can hear you and see you. You're looking very handsome today.
Perfect. Thank you very much. And we're going to talk about the diverging needs of enterprise and cloud customers. But just before we get into the subject, just a brief introduction about LightCounting. And part of what we do is we collect information on the global sales of optical transceivers around the world. And Ethernet is by far the largest market segment, but it's not the only segment where optics is being used. And when we think about the next speed for Ethernet, I think it's important also to look at what's happening beyond that, what's happening in other market segments. And in particular, if you look at the DWDM networks, we are seeing deployments of first 800 gig per wavelengths optics, which I think Sienna started more than 12 months ago, and they did pretty well last year deploying it all over the world. But at the same time, the distances for practical deployments are certainly shorter at 800 gig per wavelengths. And in the long distance networks or even metro networks, it's the efficiency of fiber utilizations that matters, which doesn't really improve much beyond 800 gig per wavelength. So I think from my understanding is that there's probably not going to be higher speeds, certainly not for longer distances used in long haul or submarine networks. So we got to reaching the barriers there. If you look at the wireless front haul market, it's going very fast to higher speeds, but it's very cost sensitive application. So we're seeing kind of tens of millions of modules deployed last year with 25 gig. 50 gig is being deployed in mid-haul, backhaul, even 200 gig is being deployed. But unless the price is well below $1 per gigabit, don't even start a conversation. So access markets tend to be very, very focused on the price, but they're getting to higher speeds, and fiber to the home is deploying 10 gig and tens of millions of units, but already looking at 50 gig PON. So, that's one contribution to the discussion. Look at what's happening outside of the Ethernet. Another contribution, let me finish with LightCounting introduction. So the reason we named LightCounting is that we count a lot of different things. So we collect data on shipments of more than 150 different types of transceiver products, for example, and that's not the only thing we do. But that's where the name LightCounting is coming from. Because LightCounting is turning 17 years old this year, so we learned how to do a lot more things over the years, and we have a team of 12 people now scattered around the world, 3 people in China, 2 in Japan, 1 in Europe, 1 in Middle East, and 5 of us in the US. So we're covering a lot more than counting transceivers. So we look at the whole supply chain of the industry, optical networking, data centers, wireless infrastructure. It's all kind of merging together into a more coherent picture, or at least we're trying to make it more coherent for our customers. But going back to the discussion for today, apart from looking at different market segments, I think it's important to look at kind of the different end user applications of Ethernet. This chart shows part of the data that we collected over the years, looking at shipments of Ethernet optical transceivers, tens of millions of units per year, looking at it from the perspective of the end users. The chart starts with 2016, because if you look back to 2010, for example, there was not much happening outside of enterprise. So Ethernet was the enterprise technology. Google was just starting to deploy 10 gig optics in decent volumes. And of course, the demand from the data centers exceeded the expectations quite rapidly. Telecom, 10 years ago, they were still deploying Sonnet SDH optics. They didn't care about Ethernet that much. Because that changed in 2016, telecom did care a lot about Ethernet, and they were the first ones to deploy 100 gigabit Ethernet. And at the time, data center vendors didn't even want to hear about 100 gig because it was so pricey and so power hungry, so they started deploying 40 gig. You go to 2020, again, things are very different, because now we're seeing the data center customers are the ones that's actually jumping on the next generation speeds, 400 gig, and telecom. I think we registered 26 units of 400 gig transceivers shipped into the telecom market in 2019, and I think it was 0 in 2020. And I think it was about 500,000 units for 400 gig for the cloud data center customers. So things change over time, and there's a good reason we only forecast the market for 5 years, because you can only extrapolate the trends for so long, because ultimately things change beyond of what you would expect. And that's the reason I kind of brought up the history. When we look at the long term, you should expect the unexpected. You can only extrapolate things for so long. And yes, we can say with confidence for the next 2-3 years that yes, the cloud companies continue to drive the market in terms of, they're going to buy more than everybody else. They're going to buy more high-speed optics than anybody else, and they're certainly going to pay a lot more for it in the future. If you look at the same chart in terms of the dollars spent, cloud already accounts for about 90% of total sales of Ethernet optics. But they're not going to pay more for it unless they can reduce the cost per bit. And they're not going to buy more of it if they can reduce their power consumption. And ultimately, why is they buying so much optics? Because, they have to keep up with the traffic growth in their data center, which conveniently is doubling every year at the moment, which correlates well with the rate the switches are improving in speed, and the optics is going up in speed. But again, don't extrapolate it for more than 5 years, because I don't think it's going to be fair to expect that the data traffic in those facilities will continue to grow so fast indefinitely. And as an example, if you look back at, say, long-haul networks, some of you may remember in 1999, 2000, AT&T was saying that traffic is doubling every year. And I think it was MCI or WorldCom was saying that traffic in their network is doubling every 100 days. Some of it might have been true, and I think, probably there were years when it was doubling every year. I think by 2010, it was certainly doubling every 2 years. 2020, long-haul networks, we're seeing a 1% growth rate, depending on who you talk to. Some people would say, yeah, it may be 10%, but in more honest discussions, you hear, well, maybe 3% is the right number for the long-haul networks. So things don't grow at the same rate over a decade, certainly not 2 decades. So things will change. Another thing is, if you look at the enterprise market, which we all lumped together in the previous chart, so here we look at applications within the enterprise segment by data rate. And the enterprises are all different. Majority of them are still staying with 1 gigabit Ethernet. And 10 years from now, some of those businesses will still be with 1 gigabit Ethernet, because that's the speed their laptops run at, and they're going to be happy with it. There is certainly increasing number of ports with 10 gig speeds sold to the enterprise market every year, and the number of ports of 10 gig ports is still increasing. Yet some enterprises are going up, and they're going up in different directions. So some of them are committed to deploying Cisco's switches, and they're using the latest 25 gig enterprise products that Cisco makes for them. But others are saying, well, if Google is doing 100 gig, we can do it as well, because we're just as smart as they are. And to be honest, the price of 100 gig optics declined so much that it's financially the right decision for many of the enterprises. So I think as we move forward with the enterprise market, we're probably going to see more diversity. And John D'Ambrosio is having an impossible job trying to please everybody with the next IEEE standards for the Ethernet. I think it's going to be impossible because everybody is different. If you look, we're going to look next at the cloud segment, and here I'm looking at 2020, again, deployments by speed, and looking 4 years from now in 2024. So certainly 100 gig is the bulk of the deployments, and this is looking in terms of number of units. So I think close to 10 million units of 100 gig transceivers shipped in 2020. And this is actually, the good news is it's actually here to stay. So we expect that 100 gig in the cloud will continue to grow. And even 4 years from now, it's going to be more than half of the market. But there is diversity. So we're seeing Google, Amazon moving to higher speeds, and they continue to do so at their own pace. As long as suppliers are willing to deliver it at a lower price per bit and the power consumption fits into the budget, they'll continue to do it. And each one of them is going to have different agenda. We talk a lot with service providers outside of the US. They have different plans, and not all of them are planning to move from one rate to the other and transfer the whole connectivity to higher rates. Some of them are liking the diversity. They're planning to have multiple data rates within the same facilities for running different applications, working with different customers. And again, as you extrapolate things going forward, things will change, because 5 years is a long time. 10 years is a very long time. So you kind of have to look at the fringes of the market to try to see what may happen beyond 5 years. And things that, look at things that grow very fast. For example, artificial intelligence is growing very fast. And the last report we published at the end of December looked at the supercomputer market and AI clusters. It's amazing how fast the systems are developing, and they're really bandwidth hungry. Data centers being bandwidth hungry. Supercomputers could easily use 10 times more bandwidth today. And 2-3 years from now, they're going to need 100 times more bandwidth. So a lot of interesting things happening there. At the same time, this AI capabilities are being brought closer to the end user into the edge data centers or central offices of service providers. And, expectations are that the wireless part of the market is going to be connected to those type of capabilities at the edge. So again, it's important to look at what's happening in the other markets and how fast they're growing to try to see, what's next for the Ethernet. And I'm using this chart from Ethernet Alliance, which is, I think, is a fantastic chart that shows how Ethernet evolved in the past, and it shows, how diverse the customer requirements are now. So there's so many different rates, and all of them are needed. I think, it would be much easier for IEEE if there was just one data rate to go with, but the reality is more complex, and customers have different needs, and they'll continue to do so. So I think the Ethernet roadmap is just going to be more crowded in the future, and this is just the reality. Another comment I would like to make is that not every data rate is going to be a home run, and it doesn't have to be a home run. I think, you look at 40 gig, there are a lot of doubts whether 40 gig should be a standard to begin with. But it ended up being very useful for cloud companies that ended up buying a lot more for 40 gigs than they planned for, partly because it took longer than expected for suppliers of optics to get the cost and the power consumption of 100 gig down low enough to make it practical. So 40 gig ended up being a very, very useful data rate. It was not a home run, but it was a solid base hit. That's probably as much as I know about baseball. But, looking at 400 gig, maybe it's going to, I'm sure it's going to be a base hit. I'm not sure if it's going to be a home run, but it doesn't have to be. And the same with, 800 gig and 1.6 terabit and beyond. Not everything has to be a home run, but go take it one step at a time, and I think you're going to do well, because if you look at what's being deployed today, we talk about 400 gig, but it's really not 400 gigabit Ethernet. It's just higher density 100 gig ports or higher density 200 gig optics that Google and Amazon are deploying. And actually, we're seeing even telecom service providers are looking at this type of deployments where 400 gig could be used in a breakout type of configuration with 4 of 100 gig connections on the other side. And, they've never seen it before. And they're saying, wow, that makes a lot of sense for us, because a lot of our equipment is still 100 gig, has a lot of 100 gig ports. And, it would be actually nice to deploy 400 gig in a breakout applications. So with that, I'm going to stop 2 minutes ahead of schedule and leave plenty of time for questions. Thank you very much.
Thank you, Vlad. I appreciate that. So I would like to call on my other panelists to get back online. Sameh and David, could you rejoin us, please?
I'm here.
You're there?
I'm here too.
Sameh,
Camera.
I think you're still a black box, David, but we'll have to live with that. We can send out pictures of you later on. So, folks, firstly, I would thank you for the very insightful stuff you came up with. So I've sort of synthesized together some questions. We do have a lot of questions, not much time. So I'm going to ask if you can try and keep your answers succinct, right? Try and go for the 3-sentence answers, not the War and Peace. So 800 gig versus 1.6T, right? Why don't we skip 800? And I think Vlad partly addressed this on the grounds that there's just different ways to put this out. So maybe, a quick round robin. Vlad, 800 versus 1.6. Why don't we just skip to 1.6?
Sorry, is that a question for me, Peter?
Yes, that's a question for you. Why don't we skip 800 and go to 1.6?
Why don't we skip 1.6?
Why don't we skip 800 and go to 1.6?
Oh, why don't we? Well, my suggestion is don't skip it, because there will be customers that's going to need 800. They're going to stay with 800. So I think going one step at a time is the right solution. And I think, start discussions on 1.6. But it would be fantastic if we could get 1.6 earlier than 5 years from now. But I think skipping the steps is not the right approach.
So this makes perfect sense to me. And if I pull you back to the slide we had before, there was the early days of perfection where everything was 10 times. And you start seeing it split apart in 2010. And since then, we've realized that we need a whole lot of rates for different places. So I think that makes perfect sense to me. I'm going to skip forward. Sameh, David, do you have any disagreement with that?
I don't have a disagreement. I think just there's a practical matter of getting 200 gig class electricals out in sort of a framework that Rakesh would be happy with. I think it's going to take quite a while, where we are going to have 100 gig electricals in the market pretty soon. That takes a long time to mature, and that gives us an 800 gig module, which leads to a nice 800 gig E. So we can feather that out to the market pretty quickly compared to 1.6, which requires everything to change.
So I can see Sameh nodding her head.
I agree with that. Yeah, I think time to market is key. That's number one. I think keep in mind that in order for us to have 1.6T, we need 200 gig on the electrical side and the optical side. And I think really it will take the ecosystem some time to get there. That's number one. Number two, there is a need for 800 gig electrical, 800 gig Mac in the market. If you extrapolate on some of the use cases, because everything is definitely end user driven, and you can see that taken for example Facebook as an example. I think my chart stops at 128 ports of 400 gig. The next implementation would be 128 ports of 800 gig, right? So that's with the 100T chip capacity. So there is a need for 800 gig. That's number one. And time to market is also key. Yeah. Okay, so I have a question I think sort of relates in here. And if we go back in history, for a long time, we ended up with this 1-lane, 4-lane approach, 1040, 2500, etc. Is this going to continue, or are we really moving towards the 1 to 8 from here on? Anyone like to take a shot at that one? I think I can start. I think we all agreed. I mean, there is a theme across all the presentations that the market need is really diverse. And so I don't think there will be just 1 or 4 lanes of something. There will be something that is based on 8 lanes or even 2 lanes. So again, as Vlad said, not everything is a home run. That's another question, right? So the high runner speeds will be probably those still based on 4 lanes of something, but the early speeds or the early adoption curve would be probably driven by speeds based on 8 lanes of something. So I don't think there is one definitive answer here.
So it's not either or, it just depends on where you are in the cycle. Vlad or David, would you like to comment on that?
Quick thing for me is just at least the on-the-wire technology 8 wavelengths and that kind of thing has proven to be a little more clunky and difficult to deal with. And so I think that there tends to be a trend towards fewer on-the-wire lanes. Now that's different from the chip-to-module interface, where at least the architectures have been doing since 100 gig E started, really easily allow you to change by power chip factors of 2. So you can go from 8 to 4 to 2 to 1, and that's the 8 we have now into the module is just a practical thing of how to build a module. So I think that part is independent.
Right. I think it's important to keep track of inflection points in the market, because if you look at, the transceiver market, I completely agree. 8 is already probably the maximum number of lanes you want to have, and the smaller the better. But if you look at co-packaged optics, Broadcom just announced their first implementations with 32 lanes per opto chiplet. And, they don't disclose exactly how they do the fiber coupling, but, they achieve, I think, if I remember correctly, what was it, 64 fibers per millimeter or something? The density could be incredible. So things change, and it's important to keep that in mind too.
So I'm glad you said that, Vlad. That leads me on to the next question I was going to ask, which is, there's been a bunch of discussion about co-packaged optics. And my real question is like, when does it really happen in general? And I think more interestingly, like, how does it affect deployment and operation in the MSDC space? And I think I'd like to ask David to chime in on that one first.
So try that again. Sorry. I missed the question.
Okay, so when does it become real? And I think my backup was I think we got it raised earlier, right? How does it affect deployment or operation in the MSDC space?
So I think it becomes real at different points for different end users, and so it depends on what curve which sort of upgrade cycle you're on. 5200, 800 or a 100, 400, 1.6 kind of thing. And that's going to change. It's going to change in what mix of interface types you need, because not all interface types are going to be available on day one. We'll probably have, something simple single mode pretty quick, but the next generation ZR is going to take a while to become practical in a module with the same density as dense 400 gig. So I don't have a good prediction for it, but there's going to be a reasonable period of time as stuff trickles out, and it'll become interesting to each of the users for very different reasons. And I think various speakers have pointed that out. Not a good answer, sorry.
So thanks, David. Sameh, can I just get your 10 cents worth on CPO?
Yes, I think it's very important to keep in mind what CPU solves as issues. So they basically solve thermal and density problems that pluggable optics will inevitably hit when we go to higher speeds. I think everyone or almost a big portion of people that I interviewed agree that with 100T chips, probably that's when we think co-packaged optics are a must, and then they will become a reality. Also, the ecosystem will have enough time to be ready by that time. But I can see some end users, some cloud service providers may have some early implementations, even with the 51.2. So that would be an early adoption, small volume, and that's because some of the hyperscalers are more power constraints than others, and also some of the hyperscalers, by choice, they wanted to start early because there is a learning curve, and they want to start early so that they can be ready when they have to be ready. But yeah, mass adoption, I think it's going to be beyond 51.2, but we may see some early adoption volume at 51.2.
All right, so I have two more things I want to cover, and we don't have a lot of time. So there was some questions about radix and I guess speeds. And if I understand correctly, what I hear get back is it's going to depend. There's going to be different people design the networks differently, so there probably is no perfect answer.
Well, right. And one thing about that is I run into a lot of people who think there is an answer. And for any given vendor, there is an answer. And they can count on that. And that's going to be true.
Is that for a vendor or is that for an operator, David?
What?
Is that for a vendor or is that for an MSDC operator?
And what I think the reality is if there's any technical inflection that happens, our current crop of big end users will be able to take advantage of it. They will take advantage of it, and they can change their architecture pretty quickly because they own their own stack. Their data center is a building scale supercomputer that is completely proprietary to first order. And so what we need to do as an industry is be careful about what they need from following the current pattern, but also don't hold back from finding inflection points and building stuff that is better on some axis, because to some extent, if you build it, people will change to it.
Okay, so David, I'm going to chop you off. So Sameh or Vlad, do you sort of go along with the idea that, radix is going to become, it's going to hook together with technology, but it's also going to depend on how you want to build your system? Make sense?
I totally agree. I mean, yes. Yeah. Do you want to keep it short? Yes, makes perfect sense. And we'll see different implementations and different choices. Yeah.
So I'm getting towards the end, so I'm going to give you one last thing for a quick comment. So Rakesh made a pretty compelling argument that power is going to be one of the key things going forwards. Very shortly, Sameh, how do you see the impact of power showing up in the market?
Absolutely. I'm glad you asked that. Yes, I mean, it's already impacting the timeline of some of the hyperscalers in terms of their ability to move to higher speeds, and it's because they are power constrained and they need to wait for different pieces of technology to work within their existing power budget. So it is already impacting the timeline of migration to higher speeds as some of the hyperscalers, and things will get only worse as we move to higher speeds.
Excellent, thank you. Vlad, just your quick 10 cents worth on the impact of how to build these things without them melting.
Well, people are already using liquid cooling to keep them from melting, and certainly if you look at the AI clusters, they're using much more powerful chips to begin with, TPUs, and they're ready to put liquid cooling on. But I completely agree that power consumption is important. The other part of the story is there are a lot of new applications that AI is starting to provide that may reduce power consumption. If there's smart technology to control the power consumption in the city, it makes sense to invest into a big data center if the overall power consumption is gonna go down. So I think again, returning to what I said earlier, I think the AI and the AI clusters within data centers are going to propel some new architectures, and we'll have to see what kind of radix they would like to use. Are they going to use some new optical technologies like optical switching? Very likely so. I think it's very likely so.
Okay, thanks, Vlad. So David, again, if you can be brusque or brief, impact of power on system building.
So I can talk about the selfish one, which is even if the end users were able to accept any power we wanted to ship them, at some point we can't build the box. We can't get enough power into it. We can't get enough heat out of it, and it doesn't scale well. We have boxes that burn more fan power than our old core routers did total, right? And that's true across the industry. So power is incredibly important just from a building standpoint, also just from an end user consumability standpoint. So I'm supportive of all of the the lower power statements.
So unfortunately, we are at the end of our time, and so I would thank all the panel, right? And because this was a lot of fun, we probably should do this again sometime. I'm sure we could have gone on for another couple of hours, but that would probably get the people on the line getting a bit bored. So I just want to quickly wrap up, folks. Let me just find the appropriate next slide. So I'd like to thank all the speakers and attendees today. This is our first virtual TEF, and I'm really optimistic that this format will make it much easier to talk to the whole community. So we are going to be making this on demand. I think that drops probably next week, so keep an eye out of it. And I think it's because we can get out to bigger people, we can get more input, which is what we really need. So on some of your invites, you should have seen there'll be an email, which is tf2021@ethernalliance.org. Or we can talk to us on your favorite social media app with a hashtag of TF2021. So tomorrow, you can see on the screen, we have the panel discussion on new applications for high bandwidths. It's moderated by my good friend, Mr. Tracy. And you're seeing Brad Booth from Microsoft, Tad Hoffmeister from Google, and Rob Stone from Facebook. You can see their topics. So I would encourage you to join for tomorrow, and also please tell your friends, because the more the merrier. So thank you for that, and I look forward to the rest of the day and hearing back from you. Thank you.